We're gonna get started. Welcome back. See some familiar faces. That's good. Today we're gonna be talking about isomers. So right here we just have this for attendance. If y'all could scan this. All right, let's get started. So isomers, stereoisomers. So stereoisomers are a type of isomer where all the atoms are connected to the same atom, but they differ in their 3D configuration. And we can see that right here between these two molecules. So it's all just a chlorine, a hydrogen, a hydroxyl, and a methyl attached to the same carbon. However, there are different molecules on the dashes and wedges, or it's like flipped. So the reason that this is important is because it can represent optical activity, and it also has like an impact on the binding to proteins. For example, in biochem, you'll learn that the D isomer of glucose is more common in the body than the L isomer of glucose. So stereoisomers are optically active compounds, and this is the case only when they are asymmetrical. So if a compound is symmetrical, it will not be an active compound. However, if it's asymmetrical and there are chiral centers, then it will be optically active. So this is the calculation for optically active molecules. You calculate enantiomeric excess, and this equation right here is how you calculate that. So it's EE equals the specific rotation of mixture over the rotation of the pure enantiomer. Now, this isn't super prevalent. You won't see this very often, but there probably will be like one or two questions like this on the exam. So it's still good to cover it. So we are going to work through this problem right here. So it states that the optical rotation of enantiomerically pure R2-butanol is negative 14 degrees. So I'm just going to write that out. And then it says calculate the ratio of R and S enantiomers in the solution if the observed rotation of the solution is positive 7. So we know the mixture is 7. So we go back to the formula. We know that EE equals mixture over here. And then you want that to be a percentage. So you're going to multiply it by 100. So in this case, if we just plug in the numbers, our mixture is 7 and our pure is 14. So you do 7 over 14 times 100, and that will give us 50%. And that number right there is telling us the S enantiomer. So that is the S2-butanol. And then the rest of the mixture, so we have 50% of just S. The rest is a perfect 50-50 of S and R. So if 50% are 50% S and R, that means that 25% will be the S and 25% will be the R. So this question is asking for the ratio of S and R enantiomers. So we'll just add up the S. That means we have 75% S and 25% R. Does that make sense? Thumbs up. We got that? Okay. This is the key. I'll just explain this. Next, we're going to look at chiral centers. Chiral centers are pretty important. You'll see them a lot in organic chemistry 1 and 2, and you'll see them in biochemistry. So it's very important that you comprehend what chiral centers are. So a chiral center is a carbon with 4 different groups on it. It's very important that there are 4 different groups. So we're looking at this right here. This carbon has 4 different groups. It has the methyl, the ethyl, the hydrogen, and the bromine. So that is a chiral center. Another thing is that the central carbon must be sp3. So if you see a double bond to a carbon, there's no way that this carbon can be a chiral center. Here are some examples of chirality. So we're looking at this one. Does this one have 4 different substituents? No, because it has these 2 methyls. Those are the same, so it's not a chiral center. What about this one? 4 different substituents? Yes. Yeah. And then is it sp3? No double bonds? Yep. So this one is a chiral center. What about this one right here? This one? No, it's not. Because it has that double bond right there. That means it's not sp3. What about this carbon right here? Is that one chiral? No. Does anyone know why?
Because there's 2 hydrogens on it.
Yeah, the 2 hydrogens are the same group, so it's not chiral. All right, assigning priority. So when there is a chiral center, you want to determine if it's R or S. And the first step of doing that is assigning priority. So the way we do this is we use the Kahn-Ingold prelog system. This states that the atom with the highest atomic number gets the highest priority. So we're looking at this example. This oxygen and this oxygen, those are higher than these carbons. If we look at the periodic table, oxygen is 8 and carbon is 6, so it's a higher one. So we automatically know that those 2 have higher priorities. However, how do we determine which one is more priority than the other? When we have the same one, we start to look at the second layer. So we look at the second layer that's right there. Over here, this oxygen is connected to a carbon, and over here, this oxygen is connected to a hydrogen. The carbon has a higher atomic number than hydrogen. So this side will have the highest priority. That's our 1, and this will be our 2. Okay, and then down here, we have a carbon and a hydrogen. Carbon is a higher atomic number than hydrogen, so that will get our 3, and the hydrogen will get our 4. It's very important when you're trying to determine R or S that you can determine which molecule has the highest priority. And you always want to write out the numbers like this. And then there are a few special cases. For example, if draw it like that. So if you have a double bond, for example, right here, the double bond counts as 2 carbons. So normally you'd be like, we look at like this example first, for example, that carbon is connected to 1 carbon. And while this one is also connected to 1 carbon, you treat it like it's connected to 2 carbons. So a double bond counts as 2 carbons, and a triple bond counts as 3 carbons. This is mentioning isotopes, but I don't think Jeske really covers those. All right, assigning R versus S. So if your priority goes in a clockwise rotation, like this, clockwise, that is R. And the way I remember that is R for right, the right way goes right. So the arrow is going to the right. And then S is just not that. So S will go to the left. Make sense? And then if you flip any of the 2 groups, for example, we flip these 2 groups, it becomes from R over here to S. Wait. S. All right, assigning R versus S. I'm going to teach y'all the methods how to do this. It's really pretty simple, and y'all should be able to understand it. pretty easily. So for example, if we have a group that looks like this, something that you always want to think about when you're assigning R versus S is that you want the lowest priority group on the dash. So if we label the priority here, we go 1, 2, 3, 4. That lowest priority group is on the wedge. That's not good. We don't want that. So in this case, when the lowest priority group is on the wedge, the way you do this is you simply assign RS the way it is. So it's going this way. It's going to the right. So it's R. And then you just flip it to S. You only do this method if the H is on, or H or any of the lowest priority groups is on the wedge. Another example. So if you have it like this, where the H is on one of the legs, it's not on a dash or a wedge. The way you do this is you do a double cross, or no, you don't. Basically, you look at where the H needs to be. So the H needs to be on the dash right there. So you bring it over there, you do a little switch, and what you do to the one side, you have to do to the other. So that would give us something like that. And then once you have the H where it is, you assign RS. So we label the oxygen as 1, 2, 3, 4. This goes in that way. So this is R. Another example. So if we have it to where the H is diagonal from where it needs to be, what you do in this circumstance is you put it where you need it. So you're going to do that flip-flop, and what you do to one side, you have to do to the other. So that gives us something like this. And then we number it 1, 2, 3, 4. And this would be R. Does that make sense? There's 3 circumstances that you will see when labeling R or S. Thumbs up if that makes sense. Yes.
Can you explain how the OH switched with the 2 carbons?
In which example? The first, the second, or the third?
The second. Oh,
You saying how this happens? So when you see how the H is right here, we need the H, since the H is the lowest priority, H is 4, we need H to be right here. So we do this little switch to get it over there. And what you do to one side, you have to do to the other side. So that puts the OH over here, and this group will go back up there. You see that? And then the H will be up there, and that methyl group that was here will go there. The only time you don't do the double switch is when the H is up here already on a wedge.
Essentially, what you're trying to do is just get the lowest priority group towards the back and put it on a dash. That's your goal every single time you want to assign R and S for these.
Is the wedge on the first one an H? It's a hydrogen, right?
Yes. Up here?
Yeah.
Yeah, that's a H.
So you can't flip it with the OH that's on the dash.
So the way you do this is when it's on the wedge, when the lowest priority group is, the way you do it is you just label it the way it is. So the way it is, it'd be R, right? Because it's going right with the OH, then 2 here, then 3 here. So after you get R, you see that H is on this. you just flip it. You make it S. So that would be S, right? Yeah.
So when assigning priority groups, use different colors.
All right. So we have some examples here. I'm just gonna do a couple of them and then I'll let y'all do the rest. So easy way to determine if there's a chiral center, if they're not asking you to find the chiral centers, is just look for where dashes and wedges are. Usually dashes and wedges are only used in chiral centers. So we're looking at this chiral center right here. So we have an oxygen, a methyl, this group, and this group. So oxygen gets 1. We know that because the rest are all carbons and oxygen has a higher atomic number. All right, and then next we're going to look at the other groups. So over here, we all have carbons on the first level, right? All carbons. So we have to go on to the next level. This one does not have a next level. So we know that that's going to be our 4. This one is the next level of going this way. And then this one is connected to 2 other carbons. However, this one is connected to 3 carbons. So this one will have higher priority. It's connected to more carbons. So this will be R2 and this will be R3. And since we have the lowest priority group already on the dash, we can just assign R or S the way it is. So we go this way. And it's going towards the left, so that's S. Oh, yeah. So we do have one more chiral center on this molecule. June just pointed it out. Great catch. But this carbon right here is a chiral center. It's connected to 3 different groups, and it has this hydrogen here. Right? Do we just pick which ones are on the dash or wedge?
I'm not sure.
It would give
Usually,
us.
usually if it's a chiral center, they will indicate with a dash and a wedge. But in this case, it's not listed, so I guess you don't have to assign RS for this one. But just know that it's a chiral center because it has 4 different groups attached to it.
All right, going on. We're going to look at this next one right here. So we look at that first layer. We have a hydrogen, we have a carbon, another carbon, and a nitrogen. Nitrogen has a higher atomic number than carbon, so nitrogen will automatically be R1. And then looking at the other ones, we have a hydrogen and then 2 carbon groups. Hydrogen is lower than the 2 carbons, so hydrogen will be R4. All right, and then comparing these 2 carbons, we have to look at what they're connected to. So this carbon has a double bond to this carbon, right? This one has a double bond to this carbon. I'll label them in red. So right now we're comparing this red carbon with this black carbon. The red carbon has an additional carbon right here, whereas this black carbon doesn't have another one. So this red carbon will get the higher priority. We'll label that 2, and this one will be 3. And then we see that the hydrogen is on the wedge here. So what we do in this circumstance is we assign RS the way it is. And in this circumstance, it goes like this. So it's going to the left. So it's S, but because the hydrogen is on the wedge, we flip that and we make it R. All right, why don't you guys try the next 2? We're gonna go ahead and walk through these problems. So looking at this chiral center right here, I'm gonna redraw it separately just so it's a little easier to visualize. Actually, no, I won't. It's fine this way. So looking at this carbon right here, we go to the first layer out. So we have this carbon, we have this carbon, and then we have, let me go more color. We have this carbon. They're all carbons, so we can't really determine which one is the highest priority. But we do know that on this molecule, there is a hydrogen, and that hydrogen will be right there on that wedge. So that hydrogen has a lower atomic number than all the rest of the carbons, so we know that the hydrogen is automatically 4. Going back to these carbons. So this blue carbon right here, remember I told you that the triple bond, it counts as 3 carbons. So it's connected to 3 carbons. This red carbon is connected to a double bond, which is 2 carbons and 1 hydrogen. And then the orange one is connected to 1 carbon, which is this one, and 2 hydrogens. So this blue one takes highest priority because it's 3 carbons. They all have high atomic numbers. This red one takes second priority, and the orange one takes third priority. So we see that the lowest priority group is on the wedge. So what we do is assign RS the way it is. So with the way this is, it goes that way. So this is S. And then because we know that the hydrogen is on the wedge, we convert that to R. So this stereo center right here is R. All right. Next, we're going to look at this stereo center right here. So we have a bromine, chlorine, and then 2 carbons. We have this carbon and we have this red carbon. So to compare bromine and chlorine, we look which one has the higher atomic number. So we're looking at the periodic table. Bromine has a higher atomic number. It's bigger. So that gets our 1. Chlorine will get 2 because it has a higher atomic number than both carbons. And then next, at these carbons, we're going to look at what these carbons are attached to. We're going to go out one more layer. So this red carbon is attached to another carbon and 2 hydrogens, whereas this blue carbon is just connected to 3 hydrogens. So this red one gets third priority, and the blue one gets 4th priority, right? So we need our 4th group, our 4th highest priority to be on that our dash. So what we do in this circumstance is we do this little switch, and we have to do it on the same side, other side, like that. So that would give us 4 here, 2 here, and then up here we'd have 1 here and 3 here. So we do our little ring, it's going towards the left. So this chiral center is S. Thumbs up, we get that? Any questions? Do we understand like that flip? Does the flip make sense? Okay. Going on to this next question. We're looking at this chiral center right here on this carbon. So we see that this carbon is attached to a nitrogen and then 2 carbons, as well as a hydrogen, which is not shown. But we know that this hydrogen is on a wedge. So using the Kahn-Ingold pre-log system, we're going to determine which has the highest priority. So this nitrogen, higher atomic number than the carbon, so that gets 1. And the hydrogen, lower than both carbons, so that gets 4. Next, we're going to look at these carbons. So this carbon is attached to an O, whereas this one is attached to another carbon. The O will take higher priority. So this one is 2, and this one is 3. Now we find RS, so this would be S. And because the fourth highest group is on that wedge, we're going to switch it to R. So R is the answer for this. Make sense? Thumbs up. Okay. That's just the answer key. All right, got another practice problem. We're gonna get started on this question. So I gave you all the hint. The first thing you want to do is to draw that ring. You want to draw it out because it'll help you identify chiral centers and it'll make it much easier to determine if they're R or S. So drawing out this ring, we know that a chair structure can also be drawn as a 6-membered ring like this. So I'm gonna put this methyl group going on this carbon. You can really choose any of them. It doesn't really matter which one's on the ring. Just make sure it's consistent throughout the molecule. So we see that this is down and equatorial. So we know that down is a dash. Next, we're going to go to this chlorine that skips 1 carbon and attaches right here. So the chlorine is going up. So we know that up is a wedge. And then we have this bromine. So that is on the next carbon going down. So we have a down bromine. And then we skip 1 carbon, we have another down bromine. And then for this group, I notice a lot of y'all making the same mistake. So the group right here is coming down and equatorial. So we have to make sure we draw it down. So we're drawing it with a dash line. And then we have this group, this group, this group, this group, H, O, the C, L, we have the NH2. That's how you should draw the 2D structure of the molecule, right? We want to remember this structure right here tells us what's going up and what's going down. It makes it a lot easier to identify chiral structures when they're in this form. So let's start at this bromine right here. So the bromine, we'll take the 1, and we'll have 2 going this way and 3 going this way. And we know that the hydrogen is there. It's on a wedge and it's 4. So assigning stereochemistry for this group, we'll go 1 to 2. So that's going to the right. But because the 4th group is on a wedge, we have to flip that. So instead of R, this group becomes S. This is S. Oh, not there. Right there. Next, let's look at this methyl group. So we're going to be looking at this carbon right here. So we know that there is a hydrogen on a wedge. So we'll look towards this blue carbon first. That blue carbon has a bromine attached. So that blue carbon will be our 1. The red carbon has another carbon attached to it. So that will be our 2. This methyl will be our 3, and the hydrogen will be the 4. So we assign this RS. What do we think this is? The way it is, do we think it's RS? Before we flip it. Is that S? Yes, it is S. But because our hydrogen is on the wedge, we're going to flip it and make it R. So this is R. Next, let's look at this other bromine. This bromine matches up with this over here. So our bromine is the 1. Then we have 2 on this side. And we have 3 over here. And then we also have a hydrogen on a wedge. So we count 1, 2, 3 going towards the left. That's S. Hydrogen is on the wedge, so we have to flip it. This becomes R. And we know that this is R. Okay. Now we're going to look at this carbon right here. So looking at this carbon, the chlorine will take 1. Then the rest are all carbons, like in the first layer. So we have to look at what these carbons are attached to. So this carbon, orange carbon, is connected to a bromine. The blue carbon is connected to a chlorine. And this red carbon is just connected to another carbon and 2 hydrogens. Because this carbon is connected to bromine, which has a higher atomic number, that will be our 2. It will take priority over this other group with the chlorine. So that will be our 3, and this will be our 4. So we have it 1, 4, 3, 2. Just simplify the drawing a little bit. Right? That's just it simplified. Looks like this. So we see that the 4 is diagonally from the wedge where we want it. So we have to do that cross swap. And that gives us something like this. And then assigning RS to that, we go this way. So that's S. This stereocenter is S. Next, we're going to look at this carbon right here with the chlorine. And one thing we want to do is draw in that hydrogen. So the chlorine will take 1. And then the surrounding groups are carbons. So we have to look at the second layer. So looking at this orange carbon, it goes to this carbon, and this red carbon over here connects to 2 other carbons. So that will be our 2. The orange carbon will be our 3, and the hydrogen will be our 4. So drawing this out, we have 1, 2, 3, 4. And again, we see that the 4th group is diagonally from our dash. So we do the cross swap. So that ends up looking like this. And then we assign this as R. So this chlorine group is R. Next, we're going to look at the nitrogen, this group. And the nitrogen will take 1. And then we have a hydrogen on a wedge, which will be our 4. Then we look at the carbons next to it. So we have this blue carbon, and we have the orange carbon. The blue carbon is connected to just another carbon, whereas the orange carbon is connected to an oxygen. So the orange carbon will take priority. So that is our 2, and this is our 3. So we assign this as R. And because the hydrogen is on a wedge, you flip that and make it S. So this group is S. We understand that? Is there anything confusing with like the cross swapping? Does that make sense? Just always want to try and get that lowest priority group on the dash. Answer key. Next, we're going to talk about,
Yep, question.
yes.
For the one with the nitrogen, is it S because the H is on the wedge? So you just leave it like that, right?
So the H is on the wedge. You label this 1, 2, 3, 4, right? So it's R. And then you have to flip it because the H is on the wedge. So that makes it S. Next, we're going to talk about isomers, specifically enantiomers, diastereomers, and meso compounds. So enantiomers are where every single chiral center swaps configuration. So if you have like all of them are R, it will now all become S, right? So, and then in diastereomers, the configuration switches at not all of the chiral centers, but some. That's a diastereo center. So like, for example, you could have one be R, the other one be R, but the other two would be S and R. So that's seen right here. It's just at least one is the same, but the rest could be different. And then meso are identical molecules that have chiral centers and symmetry. Meso compounds are not optically active because they are symmetrical. So I mentioned this a little bit earlier to some of you, but stereoisomer nomenclature, when you are naming stereoisomers, you want to put either R or S in parentheses before the molecule representing the stereoisomer. And if you have multiple stereoisomers, the way you do that is you just put the locant. So for example, like 2R before, and then comma 3S. And then you go on naming it. Make sense? Pretty simple. All right, so call these molecules either constitutional isomers, enantiomers, diastereomers, or identical. I'll go through the first one with y'all, just to show y'all how I want it done. So first thing I would do with this is I would convert this chair structure into a 2D structure. So draw out that ring. We see that we have a bromine going up. And we have a chlorine that is 1, 2 carbons going up. So after drawing it like this, I see that the chlorines are the same. They're both coming out towards us, and they are both they're both R. So chlorine is R, and this chlorine is R. Next, looking at the bromines, the bromine is this bromine is R, and this bromine is S. So we see that one of them is the same and one of them is different. That is the definition of diastereomers. Go ahead and try out the second one. I'm going to go ahead and cover this problem. So the first thing you want to do is draw out this Newman structure. So we know that this is a carbon, that's that central carbon. We have the OH going up. We have the bromine going back. And we have that methyl going towards us. And then we draw out that back carbon. We see that bromine's going down. We have a methyl going towards us, and we have an OH in the back. So the way I would do this is assign RS for each of the stereocenters and then compare them. So for this first one, we have OH as, no. we have Br as 1. We have that OH group as 2. This would be 3, and the methyl would be 4. So assigning R or S to that, it would give us R, and then we flip it because the lowest priority group is on that wedge. So that becomes S. And then for this back one, we have bromine 1, oxygen 2. This is our 3, and then our 4 is up here. So we have that 1, 2, 3 going that way. So S, but because our lowest group is on this wedge, it becomes R. So we have S and R as our chiral centers for that molecule. Looking at the one we're comparing it to, we have bromine 1, OH2. This is R3, and the methyl as 4. So we go this way, that's S. And because the methyl, our lowest priority group, is on that wedge, we flip it, it becomes R. So already we know that these aren't identical because that first chiral center is different. And then for this second one, we have Br1, we have that OH2, this is our 3, and that's our 4. So we go this way, that's R, and it becomes S. So we have R and S.
So
R.
yeah, R, because the methyl is in the back.
Oh, my mistake. So the lowest priority group is already on the dash, so we just keep it the way it is. So that stays as R. So comparing these, we have SR versus RR. RR, I sound like a pirate. But so that makes these diastereomers. Me in one piece.
You can also you can also mention that you can solve it the other way where you can draw the image for the second one, compare substituents.
I don't know how to do it like
Oh,
that.
you know,
No, I don't do it like
we'll
that.
show if you want.
So that's the answer, Keith. That's what we just said. All right, got some more practice. Let's go over these problems. So first thing I would do for the first problem is draw it out. So we have the carboxylic acid. That's what this is. We have that going up. And we have this to represent the back carbon for now. But then we have a Br coming towards us and an H going towards the back. And on the back carbon, we have a carboxylic acid going down. We have a hydrogen going towards us and a bromine in the back. So assigning. Thanks. Okay, so we're going to look at this first carbon here first, right here. So we'll label the Br as 1. This carboxylic acid will be our 2. Wait, no. My mistake. So we have a carbon here. We have this orange carbon. We have this red carbon. We can compare. So this red carbon is connected to the oxygen, but the orange carbon is connected to a bromine. Bromine is bigger than oxygen, so that will be our 2. Oxygen will be our 3, and this hydrogen will be our 4. So assigning RS, this goes that way to the left. So this is S. Next, we're going to look at this second chiral center. We're going to look at this one. So we got this bromine as our 1. Same thing as the previous. We have this group right here as our 2. This is our 3 and the 4 right there. So this goes to the left. So I make it S, but because the hydrogen is on that wedge, we flip it and make it R. So we have S and R. Next, we're going to look at this molecule we're comparing it to. Bromine is 1. This is our 2. This is our 3, and this is our 4. So that goes that way. S. Okay. And then this other carbon right there, bromine 1, 2, 3, 4. So we go this way, S, but because that hydrogen is on the wedge, we flip it and make it R. So we see that the molecules, they have the same molecules and they have the same configuration. So these are identical. Next, we're going to look at this problem. So we're looking at this chiral center right here. So we know that we have a hydrogen on a dash back there. So that hydrogen will be our 4. And then next, we're going to have to compare these carbons. So we have that blue carbon, we have the red carbon, and we have this orange carbon. We can automatically tell that that blue carbon is going to be our 3 because it's not connected to anything else. Next, we're going to compare the red and the orange carbon. So the red is connected to 2 carbons and 1 hydrogen, but so is the orange. The orange is also connected to 2 carbons and 1 hydrogen. So we need to go out one more layer. So out here, these are both connected to 3 hydrogens, whereas these are connected to 2 carbons. So this orange carbon will get our 2, and the red will get the 3. No, sorry. Red will be 2, and orange is 1. There we go. And then assigning our S, this goes to the left, So that's S. And then this other stereo center right here. Oh, yeah. A mistake. This is a common mistake. This is not a stereo center. This is one of the examples where you'll see a dash or a wedge and it not be a stereo center. Because these 2 groups are the same. So it's not a chiral center. Next, we're going to look at this one right here. Me thinking now, making sure it's a chiral center.
Yeah, this one's missing these 2.
It's okay. We'll just be different. But all right. So first thing we're gonna do, we know that we have a hydrogen right here on this wedge. That will be our 4. We see that this methyl will be our 3. This will be our 1, and this is our 2. So we go this way. That becomes R. And because the hydrogen is on that wedge, we flip it, and it becomes S. So this is S, and then we look at this one.
It's a typo. It's supposed to have the isopropyl like this, but
Oh, okay.
that's just drawn.
All right, so there's a typo on this question. We'll get that fixed when we post the slides, but that should be like that, right? So there is no stereo center right there. So because these are both S, they have the same amount of carbons, they are identical. And we can see that because if we rotate this bond right here, it will produce that. It's simply just a bond being rotated. Single bonds, they can rotate freely. Double and triple bonds cannot rotate. All right, so I'm gonna have y'all draw all possible enantiomers. There is a method for this. So the first thing you want to do, I'll do this first question with y'all, is determine all chiral centers. So looking at this molecule, can anyone tell me how many chiral centers there are? Two? Yes, two. And those are right here. So the way to determine how many enantiomers there are, you use the formula 2 to the n, with n being the number of chiral centers. Okay, so we see that there's two chiral centers, so that means there's four possible enantiomers. So the first one is we can draw this like this, right? And then we can draw it like this. We can draw it like this, or like this. Now, I'll wait for a sec so I can get this copy done. These two molecules, these are meso compounds. We know that because they have chiral centers and they are symmetrical. They're meso compounds. So what Jesky will want you to do is to cross out one of these because they're identical. They're the exact same. They're not really enantiomers. You can take one and pancake flip it and make the other one. Make sense?
Can you guys see where the symmetry is as well? Like if you draw a line of symmetry,
Symmetry goes that way.
yeah. That's what it means by symmetry.
All right, I'm gonna have y'all try the next. Yes. I'm gonna go ahead and cover these problems. There is a little sneaky thing about this problem. Let's see how many of y'all got it. All right, so we have two chiral centers. We see that there's a chiral center here and there's a chiral center there, right? So we use the formula 2 to the n. We know that there's 4 enantiomers. So the first one, we can have this. Then we can have this. We can have this. Or this. Now, an important thing to notice about this molecule is that if you are to rotate this molecule along this bond right here, you rotate it, it will make that, right? You spin that little single bond up. So what's in front of you is now to the back. You can do the same thing with this one. And if you were to rotate this down, it would make this. So these two are meso compounds. They're symmetrical and they have symmetry and they have two chiral centers. So you can just cross one of these off. Does that make sense? Rotating that single bond? Yes.
You can't cross off as the same thing. Like they both have wedge and they both have. Yes.
Well, because if you are to rotate this bond right here, it will form this. That's different. right? Because if you do it to this one, it's going to form that. Those are different, right? But these ones, you can rotate them to be the exact same.
Notice how in the first two pairs, you can't draw a line of symmetry. And a line of symmetry is indicative that it's going to be a mesel compound, and mesel compounds are the only ones you can cross out the identical ones.
Nope. Answer. All right, now we're going to talk about cis-trans isomers. These mainly refer to alkenes. Alkenes are double bonds. So a cis isomer is both high priority atoms are on the same side. We can see that right here. And a trans isomer is them on the opposite sides. Now, we won't really use cis-trans that often in organic chemistry. What we use instead is E and Z. So the way I like to remember this is Z for Zame. Z is the Zame side. E is different. Like E is not Zame. So, and what we're talking about being the Zame is the high priority atom groups, right? So we look at this example, the high priority groups are on the Zame side. So that's Z. This one, they're opposite, they're E.
It's a bit goofy, but it's a good way to remember.
Yeah, y'all will remember it because y'all be like, that's silly.
Oh, really? Yeah.
Wait, what?
Jessica says it a lot too.
Yeah, a good way to remember it. But yeah, that's pretty much how you use it. And when you see an alkene in a naming question, you'll put like the E at the beginning.
Locant.
Yeah, and the locant if there's multiple.
Naming E and Z.
Have you started on it?
I don't have any practice problems for that.
We can make one right now.
Yeah.
All right, so let me name. Just draw that, do like L, do like that. All right, so when you're naming alkenes, so you find the parent chain first. So we have 1, 2, 3, 4, 5, 6, 7. Instead of octane, it becomes octene. Oh yeah, heptene. My mistake. Right. And then you want to number it in the way so that the alkene has the lowest possible value. So we can either name it like this, or we can name it this way. So the black numbers have it starting on 3 instead of starting on 4. So you will number it with the black numbers. And then we look at it, we see that on the alkene, they're on different sides, right? So that's E. We're going to put E at the beginning. And then we have to name this stereocenter. So we have chlorine as 1, this is 2, this is 3. So that is R. So we have R, and then we have 2 chloro for our substituents, 6 methyl, and then you put the locant of the double bond, and you choose the lower number. So it'd be 3 heptene. Make sense? All right, next we're going to talk about constitutional isomers. Constitutional isomers differ in how they're connected, but have the same formula. So you see like this is C6H14, this is C6H14, and this is C6H14. So draw some isomers for C4H10O. We're going to go over this. So this is almost kind of like guess and check. I don't know if I have like really good methods for this, but you do want to start out with an easy way to do this is start out with 4 carbons because you know you have 4 carbons, and then you can just connect that to an O because you know you need an O. And just looking at this, we have 3 hydrogens, 2 hydrogens, 2 hydrogens, and 2 hydrogens. So that is 5, 7, 9. We need one more hydrogen to match the formula. You can just stick it on the H. And that gives us one with the alcohol. Again, we can start out with our 4 carbons, and then we'll just attach an O somewhere, right? So we have 3 hydrogens, 2 hydrogens, 1 hydrogen, 3. So that is 9 again. So we need one more hydrogen. We can stick it on the O. That's another one with the OH group or an alcohol. And then to come up with one with an ether, we could just draw an ether with 4 carbons. And looking at this, we have 4 carbons and oxygen, and then counting the hydrogens, we have 3, 6, 8, 10. So that matches the formula. And then another one for the ether, we could try and draw this, right? It's 4 carbons and it has the oxygen. So we have 3, 5, 7, and 10. So those are 2 possible constitutional isomers. There's definitely many more you could get, maybe like 3 or 4 more. But yeah, those are some of the possible structures you could have gotten. All right, that's all we have for today.